Thanks you for the kind introduction. Unfortunately, what he said is wrong. I'm not the best one to explain it. So again, you chose wrong. Yeah, I'm sorry. So, yeah, I think Pedro will be the best one to explain it. Anyway, so we'll start today with the basics of AdS CFT. So today there will be no supersymmetry, no integrability. So very simple. I'll try to explain the basic idea behind AdS CFT. And then probably for the next two lectures, if you have many more questions about this, I can try to answer them in the next lecture. So otherwise, I'll go into describing more how to use integrability to analyze some problems in AdS CFT. And there we will definitely use supersymmetry in the theme of this school. Okay, so AdS CFT is really, I think, a bad name. So the subject should be called the quantum field theory / quantum gravity duality. But sometimes it's also called the gauge gravity duality for reasons that will be clear in a second. And the basic idea is an equality between, you take a space-time and you consider quantum gravity in this space-time, in the interior of this space-time, so this whole interior. And then this should be equal to a certain quantum field theory that is defined on the boundary of that space-time. Okay, so that's the AdS, this quantum field theory / quantum gravity duality is just this statement, the statement that these two things are equal. Now, we have various examples where we'll give a specific space-time here and a specific gravity theory and a specific quantum field theory on the boundary. And there are various examples of this. So many of the examples involve string theories. So that's string theory is a way of quantizing gravity. And when we have strings, so if we have strings here in the interior, in particular if we have weakly coupled strings, which is one regime of quantum gravity, then typically the gauge theory that is dual to it will be a UN gauge theory. A UN gauge theory, usually in the Lorentzian limit. So, and you need to be in the Lorentzian limit because here strings have a coupling, and the coupling between the strings turns out to be proportional to 1 over n squared. Now, the reason this is the coupling comes, it's due to an old argument of Toft that if you have a UN gauge theory, you can divide the diagrams, the Feynman diagrams of that gauge theory, into planar diagrams and non-planar diagrams. And non-planar diagrams are suppressed by powers of 1 over n squared. And this amounts to, and it turns out to be exactly the same as the division we have here in string theory between string wall sheets which have the topology of the sphere or string wall sheets which have more complicated topologies, which represent string interactions. Okay, that was a very quick review of the Toft argument, but basically since that argument, it was expected that Lorentzian gauge theories should be related to string theories of some kind. And people thought, well, maybe those are string theories that somehow live in 4 dimensions, the same number of, for example, if you started with a gauge theory in 4 dimensions, people expected those strings to live in 4 dimensions, but actually those strings should be thought of as living in some higher dimensional space. In fact, they live in the interior of this other space-time. Now, in gauge theories, we usually have a gauge coupling, and so there is the Young-Mills coupling, not to be confused with the string coupling. And the effective coupling in a Lorentzian gauge theory is G square n, And the reason for that is that we can have n colored objects or n gluons propagating between that can transmit the force, and so interactions are n times bigger than you would otherwise expect. So, so in other words, if you have the propagation, for example, of a gluon, and you have this type of diagram, there is a color line here which can have n different colors, and for that reason, this diagram gets enhanced by a factor of n. So really, the effective coupling of these theories is g² n, and so if you have a large n-gauge theory, this will be the coupling. So whenever lambda, and this is sometimes called the 't Hooft coupling lambda, and when lambda is small, the gauge theory will be weakly coupled. And it turns out that in this relationship, the radius of the space here, so some measure of the typical curvature radius, I'll be more concrete in a second, the radius of curvature of the space, that is somehow the size of the space, in string units is typically a power of g² n to some positive number here. Now, the fact, so string theory can be well approximated by gravity whenever this number is very big. So whenever the size of the space is much bigger than the string scale. So in other words, the picture is something like this. So we have some very big space, and the graviton is a little string whose size is of order the length of the string. And in order for you to be able to approximate the string state by a point-like particle, such as the graviton of Einstein's theory, you need that the size of your space is much bigger than the string scale. Okay? So gravity will be a good approximation whenever this is much bigger than 1. And I said before that perturbative gauge theories or weakly coupled gauge theories, the Euryushian intuition of gluons moving almost freely, interacting now and then, is good when this is very small. Okay? So now the regime where these two theories, these two approximations are easy is perfectly incompatible, and that's good news, because otherwise we would have ruled it out immediately, because the theory here doesn't look anything like perturbative gauge theory. And that's also why it's called the duality. So that's where the word duality comes from, is the fact that the parameter space is divided into two regions, and in one region of parameter space, one description is simple. In the other region of parameter space, the other description is simple. Okay? So here, in one regime, perturbative gauge theory is simple. When lambda is small, when lambda is large, the string theory description is correct. Okay. So that's the basic statement, and we'll give more and more, we'll specify it more and more. So that's somehow the basic story. Now, in order to understand this a little better, one needs to understand better what kinds of spaces we're going to be talking about here. And the spaces are spaces which have something called the warp factor. Warp factor is just simply a gravitational potential. So there are spaces where, for example, if we start with a theory which is defined in R4, so we have the time, this is R3, 1, and they have an extra dimension, let's say c². And then we have here a gravitational potential, which depends on the coordinate c. This is just some overall factor of the metric. When a factor multiplies the metric in this Lorentz invariant form, it's sometimes called warp factor. You might be also used to redshift factors, which are factors that just multiply the time direction, and so on. Now, what happens when you have a situation like this? Well, just let me. So the types of metrics we'll consider, this factor will be such that it diverges for c equal to 0. So there's some region where it blows up. And then in some examples, the simplest examples, like the ones that have most symmetry, they just decrease continuously. But for the purposes of illustration, let's imagine a situation where this warp factor just goes up again. Okay? Now imagine you have gravity in a situation like this. You have a warp factor that has a minimum at some location. Okay, this is just simply gravity. This is a gravitational potential well. So if you put in a particle somewhere, its energy, let's say you put it at rest at some position C, its energy would just simply be the rest mass of the particle times the local value of the warp factor, W of C, right? And the particle will want to go to the region where the warp factor is minimized. So the particle will want to sit here at the bottom. Okay? That's a gravitational potential well. Now, imagine we have a situation like this, and we concentrate on the lowest modes. So we concentrate on the modes where the particle is just stuck here and moving purely in the 4-dimensional directions. So then clearly the physics of this particle, this particle will behave as a 4-dimensional particle, right? Now, if we do quantum mechanics, of course, this particle will have some wave function, and it will have a wave function localized near the minimum of the potential. And again, from the 5-dimensional theory, we go to a 4-dimensional theory. Now, this is nothing surprising. You, of course, know that in many situations, let's say in condensed matter, for example, you have electrons moving, let's say, in a 2-dimensional, confined to a 2-dimensional layer by a potential in, let's say, the C direction, and they behave as 2-dimensional particles. So that's fine, nothing surprising here. Now imagine we start including the higher modes. So there is this wave function, and then there are some other wave functions where it oscillates twice, and so on, right? So these are all the higher modes representing the radial oscillations of this particle, right? This is more or less like a particle in a harmonic oscillator. Will have all these various modes. So then you would say, well, you have a certain 4-dimensional field theory with an infinite number of particles, you would say, because you have an infinite number of particles because you have all these various Kaluza-Klein modes, right? Okay. Now, this is what you would naively say. Naively, you have an infinite number of 4-dimensional particles. And now this fact that you have an infinite number is the reason why if you have a quantum field theory, let's say on a box, and you want to include, and you want to treat it as a field theory in 1 less dimensions, well, it's useful as long as you consider energy scales less than the box. When you consider energy scales higher than the size of the box, it's convenient to go to the higher dimensional field theory. And it's not convenient to think of it as a field theory which includes all this infinite number of particles. Okay. Now, what happens in a theory of gravity is that there is a kind of truncation. A kind of truncation that allows you to keep what essentially is a finite number of fields. So you are able to describe this whole configuration, this whole set of states and so on, everything in it, in terms of a finite number of fields. And, well, there are various qualitative reasons why this happens. One is the so-called holographic principle that tells you can describe the degrees of freedom in some region of space by a number which goes like the area. Another, more practical, is that if you try to excite here very high Kaluza-Klein modes, you might end up forming a black hole, and that truncates them. And in fact, in this duality this duality we are talking about, this UN gauge theory has large by finite n, so there's a finite number of degrees of freedom, which is described in the 5-dimensional space-time. Okay, and this finite number of fields, this number of fields is turns out to be proportional. I'll explain later why it is proportional to this. I'm now just giving results. It's proportional to the radius of curvature of this space. Well, it's proportional to the inverse of the Newton constant, the 5-dimensional Newton constant, in units of the radius of curvature of the space. So that's the finite number of fields you need to include. Now, a very special case of this relationship. Now, you shouldn't be confused by thinking, perhaps my explanation was a little misleading, in that you shouldn't think of these fields that will describe the field theory as being directly these Kaluza-Klein modes. We'll see that these Kaluza-Klein modes we're talking about here are really bound states of the fundamental fields. All that I wanted to illustrate here is just this truncation in the number of fields and why it's important to have gravity. Actually, in one of the exercises, I proposed that you demonstrate that if you have here an ordinary quantum field theory, then it cannot be dual to a quantum field theory on the boundary. Okay, so it's crucial to have gravity in the bulk. Now let's consider a special case. And a special case is a situation where this warp factor W is equal to 1 over C. Okay, so in this situation, we have a gravitational potential of this kind. And the metric in this situation has an extra symmetry. So we have all the four-dimensional directions plus the extra direction divided by C squared. Okay, so that's the metric. And this metric has a rescaling symmetry. So if x goes to lambda x and c goes to lambda c, this metric remains, the metric remains of the same form. So that's an isometry of the metric. And this will translate into a symmetry of the boundary theory. So in this case, the boundary corresponds to these directions, the four-dimensional directions. So the boundary is whatever sits at c equal to 0. So in general, the boundary occurs whenever the warp factor diverges. And when it diverges in this particular way, the theory is conformal in the ultraviolet. So if it behaves like this near the boundary, you'll have a field theory which is scale invariant. Because this bulk symmetry, so the fact that we have this symmetry in the bulk theory, translates into a symmetry of the field theory, and that symmetry is just symmetry under rescalings. Okay. Now let me continue talking about the physics of this warp factor. The most important thing to understand in the gauge gravity duality, or one very important thing to understand, is the significance of this scale factor, what it does to the physics, and what happens under this very big gravitational potential that we have. So let's try to understand what happens to a massive particle. So we discussed before the fact that if we put a massive particle here at some point on this potential, it will have an energy measured with respect to that time. So here, so there is the time t, and we have time translation symmetry under translations of this time t. And if we measure energies conjugate to this time translation, so we have the operator that implements those translations in the Hilbert space, blah, blah, blah. If we measure energies conjugate to this, we'll find that the energy of a particle at position C is just given by, well, the same formula I written before, mr times divided by C0. Okay, so if this is a particle sitting at some position C0, that will be the energy at that position. Of course, if we put a particle at this position C0, it has a gravitational force and it will start moving in, right? So a particle put at this position will start moving to the interior of AdS. And if a particle has this energy and it comes from the interior, it will reach to this point and then bounce back. Okay? So a massive particle will never be able to get to C equal to 0. Okay? So it will always bounce back before it gets to this boundary. So we said that C equal to 0 was a boundary. Notice that this is a place where you can't quite reach with massive particles. You try to send a particle at higher and higher energies, and you get closer and closer to C equal to 0, but you bounce back before you get to C equal to 0. With massless particles, it's slightly different. So massless particle, in principle, can, a massless geodesic can get to z equal to 0. And the easiest way to see that is to look again at this metric and notice that a massless particle doesn't care that there is this factor 1 over c squared. And then you find that you have really half space. I mean, you have in the z direction, a light ray can come and then go back out. Okay? But really, I mean, they can do it, but at the cost. I mean, when they get here, they are really, really very redshifted. And by putting a simple boundary condition here, and we'll specify later the boundary conditions, also massless particles go back in. And in general, we'll have to supply some extra boundary condition here at the boundary of AdS to tell us how these massless particles are reflected. Okay. Now notice that as we move this particle to smaller and smaller values of C naught, it will have higher and higher energies. And this is the first manifestation of something which is we'll see later in more detail, which is the fact that approaching the boundary of AdS corresponds to going to very high energies in the boundary, especially very high energies, off-shell energies in the boundary theory. Now, this can also be seen by noticing that if you take the scaling symmetry and you perform rescalings that move you to smaller values of C, that is, you choose here lambdas which are smaller than 1, then you're also going to x's that are smaller than 1. So in the boundary theory, you are shrinking your distances. You are examining the UV behavior of the theory. Now, in fact, it turns out that if you have a particle at some position C0, so a massive particle at some position C0, it corresponds in the boundary theory to some object, some bound state, some state in the field theory, which has some characteristic size, which is also proportional to C0. And again, this is also due to this, just simply the application of this symmetry. So if C0 corresponds to some object of some size, then as we rescale it, it will rescale together with C0. So sizes here on the boundary theory correspond to this distance from the boundary in the bulk. So a point-like particle in the bulk corresponds to an object that has some non-zero size in the boundary. And as we approach the boundary, this object shrinks and becomes smaller. Okay. Now, this is also one way to think about the emergence of the extra dimension. The fact that in a scale invariant theory, in order to specify the state of some object, you need to give not only the center of mass position, but also its size. And so you need one more coordinate than you would naively have expected. And this one more coordinate is this extra position in the z direction. Okay. Now, let's talk a little more about this space. It's called, this space, it's called anti-de Sitter space. I think I already said it. It's the simplest space with constant negative curvature. And it has more symmetries than they are apparent in this way of writing the metric. So I've written the metric in such a way that you see the Poincare symmetries plus the rescaling that I've just mentioned. But it has a few other symmetries which are called special conformal transformations, and so on. So by writing the metric, unfortunately, there is no coordinate system that makes all the symmetries manifest. So you'll have different coordinate systems make different symmetries manifest. Okay, so, but there is another set of coordinates that are particularly useful for thinking about anti-de Sitter space. And these are coordinates where the metric takes the form d tau squared cosine hyperbolic of rho plus d rho squared plus sine hyperbolic of rho squared the omega 3 squared. We are talking about the 5-dimensional anti-de Sitter space now. There is some overall factor which is telling us the radius of curvature of the space. We have the metric of the sphere. This would be the radius of the sphere. This is just setting the scale of the space. And so in these coordinates, the space can be, actually, in fact, the Penrose diagram of the space can be represented as a cylinder with one time dimension. And then this circle here is really the S3. And then we also have the radial direction that starts from the origin of the cylinder. Okay. Now imagine we consider a Euclidean field theory for the time being. So a Euclidean field theory will be related to Euclidean AdS space. And Euclidean AdS space also is known as hyperbolic space. It's the same, you can represent it in the same way, but with a plus sign here. Yes?
The term you have multiplying d tau squared, is that ln? What is that?
Hyperbolic cosine. I'm sorry, I learned with Russian books, which write this as... yeah, sorry. Sorry about that. Okay, so if you have the Euclidean field theory, then you can map the Euclidean field theory to a cylinder by considering something called radial quantization. So you start with some origin, and you think of time not as slicing the theory in this way, but slicing the theory at different radii. Okay. Now here the size of the sphere is changing, but we have, of course, the conformal symmetry that allows us to change the overall scale factor in the metric. So this is now the metric of the 4-dimensional field theory in Euclidean space. We can multiply this metric, divide this metric by r squared, and so we get here log of r squared. Now we have a cylinder, Euclidean cylinder. Okay. And then the theory on this Euclidean cylinder is dual to the theory on the Euclidean version of this space, which we could also, now we could analytically continue the time coordinate in this cylinder to Lorentzian signature, and we would have this Lorentzian signature space. Now the reason I mentioned this, this relationship in detail between the plane and the cylinder is the fact that if you start with the quantum field theory on the plane and do this mapping, here you get the theory on the cylinder on its ground state. So you get the ground state of the theory on the cylinder, the state with lowest possible energy. But by inserting local operators here, so you insert some operators at the origin, and you do the same mapping, then here you get some excited states of the theory on the sphere. So you have this, this mapping between operators in R4 and states of the theory on, well, on S3 times time. Okay. So this is something that is true in any conformal field theory in 4 dimensions, but it's actually true in any dimensions. You have to only change the dimensions here of the cylinder. And it follows just from the simple argument about the Weyl rescaling symmetry of the theory. The rescaling of, in a conformal field theory, you can change the metric by any overall factor, and the physics will be the same. Okay? Up to something called the conformal anomaly, which is not important for what I'm saying here. Okay, so now we have this mapping between states, operators and states. Of course, here we had this AdS space. Now we can view the field theory as living on the boundary. So this is just the boundary of the cylinder. This is a cylinder with the interior, and this is the cylinder without the interior. That's where the field theory lives. And different states here correspond to different states here in the bulk. So in particular, imagine you have a particle here sitting at the center of AdS. So you have some particle, and we can compute the energy of this particle with respect to that time coordinate that appears in that metric. And so the energy of that particle will be m times the radius of AdS if it's sitting at the origin. Now, and that will be the energy of the corresponding state here on the boundary theory. And such energies are related to the behavior of the state and their translations in this direction, which is the same as the rescalings of this coordinate r. And so that eigenvalue is the same as the conformal dimension of these operators. Okay. So those energies are the same as the conformal dimension, usually denoted by delta, is the dimension of the operator. Well, it's how the operator scales and their rescalings of the coordinates. So we have this relationship between the operator dimensions and the energies of particles. Now, of course, when we did this for a massive particle, and I've ignored quantum effects, so I ignored the fact that this particle can move and has some wave function. So, in other words, notice here that this gravitational potential, again, is like some harmonic oscillator potential. Well, it's not really harmonic, anharmonic, let's say. But it's some potential. And due to quantum effects, there will be some quantum contribution to the energy of the particle. And you can do that quantum mechanics, and it just simply corresponds to solving the wave equation for a massive field on this curved space. And you can calculate that energy precisely, and you'll get the precise expression, which for a scalar field has the form 2 plus square root of mr squared plus 4. So I'm not telling you how, so this is the full exact answer. So it's exact in the regime where you can calculate. Well, it's not quite exact. I mean, it's only exact in the approximation where you take into account the quantum mechanical effects of the particles, but you do not take into account the back reaction of the particle on the geometry. Okay. Good. Now, this formula shows a couple of features that so first is consider a massless particle. So particle m equal to 0. That would correspond to an operator of dimension delta equal to 4. So first thing to notice is that a particle with 0 mass does not lead to a state with 0 energy because of the ground. In that case, the only contribution is just the ground state contribution from the harmonic oscillator potential. So there is that contribution to the energy, and that contributes to a non-zero energy, an energy equal to 4 in these units. Notice, by the way, that the spread of the wave function here is, if this has some curvature scale of order 1, the spread of the wave function will be, again, of order the radius of the radius of curvature, right? Just even in the original formula that is some energy which goes like the gradient terms you need for curving, so changing the wave function at scales of order the radius of curvature that contribute with a mass or energy of order 1 over r that give a contribution to the energy of order 1. These are the corrections we have to take into account when we do the quantum mechanical calculation. Anyway, so mass equal to 0 will still have non-zero energy, delta equal to 4. Now, delta equal to 4 in a 4-dimensional field theory is a special dimension because this is a dimension of a so-called marginal operator. So we can add this operator to the theory, at least to leading order, the theory will remain conformal. So this is a perturbation which, at least at first order in the strength of perturbation, it does not change conformal symmetry. Now, there are many situations where we have scalar fields with a completely flat potential in the bulk. The dilaton, for example, in some of the examples in string theory, will be an example of that. And in such situations where we have no potential for the dilaton and the dilaton have any value, so the scalar field can have any value, so the theory will be conformal for any value of the dilaton, and changing the value of the dilaton would correspond to changing the constant value of that scalar field everywhere in space. Okay, that's what that corresponds to. Yeah.
How do you know that it's exactly marginal?
yeah, that requires more calculation. That's why I said if you have a potential which is exactly flat, then it will be exactly marginal. Yeah, exactly. That would require more calculation. There are many situations where you have delta equal to 4 states, but they are not all marginal. Not all exactly marginal. Now, another interesting case is the case of the graviton. So the graviton, again, is a mass particle which in the bulk has mass equal to 0, but now has spin 2. And it also leads to dimension 4 state, which is just the stress tensor operator on the boundary theory. And that's the correct dimension of the stress tensor. Okay. So I mentioned a couple of states. So in any conformal field theory, you'll definitely have the stress tensor. So it will have the graviton in the bulk. Okay. So that's a state that we'll always have. And then different other quantum field theories could have other states. Now, let's analyze what other states we get from the point of view of the bulk. Well, I mentioned that in many examples we have string theories. So string theories contain string states. And among the string states, there are the massless string states, about which we talked a bit here about. So we have those. But in addition, we have massive string states. We have a mass of the order of 1 over the string length. Remind you that the string length is, so the tension of the string is 1 over Ls squared. So that's the definition of Ls. So you have a string of this tension, will have such states, and it will lead to operators of dimension R over Ls. Okay? So all the massive string states will have dimensions which scale like R over Ls. And if you recall what we discussed here, so we discussed that the gravity approximation will be correct precisely when R over Ls is very big. So precisely when all these states have high dimensions. Now, if you go to just the first massive string state, you'll find that among those massive string states, there are states we have spin bigger than 2. So we have, for example, states of spin 4, just the first massive string state. So now, if this state was very light, then gravity would not be a good approximation. You have sort of light states of spin 2, spin 4. You probably are forced to include all kinds of spins. So the demand that delta over Ls is very big is given a high mass to all the states we have higher spin bigger than 2. And make sure that what remains are all the states with spin 2, and therefore, certainly in flat space, the only consistent interactions of low energies of spin 2 particles are those of gravity. So this leads to a natural idea that if perhaps you have a conformal field theory where all particles of spin bigger than 2 have very high conformal dimensions, you probably discover gravity in the infrared, though this is a conjecture, it hasn't been proven. Anyway, so but this is something to remember. In particular, is saying why if you had why QCD, for example, will not have a nice gravity dual even for n equal to infinity, because there we expect to have higher spin particles, like the resonances we see, which have spin bigger than 2, and which are not much heavier than particles with spin less or equal to 2. Anyway, so the gravity approximation will not be arbitrarily good in those cases. Of course, the string approximation will be correct. Now, there is one important property of the spectrum that I didn't mention, and it's the fact that in a weakly coupled string theory or in a theory of gravity that for large radius, you can separate the states according to single particle states and multi-particle states. So in other words, the states can be organized according to at least an approximate Fock space, where you have the state of one particle, then you can add one particle, will have some energy E, let's say, E for the one particle states. And then you can have two particle states, which will have energy, well, the energy of the first particle you put in, the energy of the second particle, plus some small corrections. So in a theory of gravity, the small correction will be proportional to the Newton constant in the theory. In these theories we're talking, when in the gauge theory will be proportional, the correction will be proportional to 1 over n squared. And this structure of large n gauge theories arises when you consider when you consider single trace operators, so operators which can be written in terms of many insertions of the field, versus operators which are of this form, for example. So you can consider an operator which contains two traces, and versus these operators. Now, if you're in the large n limit in the regime where the 't Hooft coupling is fixed, you can compute the anomalous dimensions of these operators, and that will be a typically hard calculation. And my next two lectures will be about computing the dimensions of these operators. But then the dimensions of these operators will be just the sum of the dimension of this operator plus this operator plus some small correction. Okay. And again, this is a structure which matches the gravity structure, and it essentially boils down to the same thing I mentioned here about planar diagrams. So that large n theories in the planar approximation correspond to string theories, again, in the approximation, tree-level approximation. That we have this expansion in terms of the genus of the diagrams translates into the statement that we have the expansion in terms of the genus of the world sheet. Okay. Now, can a weakly coupled theory ever have a gravity dual? Well, a weakly coupled theory always contains, a weakly coupled gauge theory always contains operators of this form, d plus to the s phi, where let's say you have two operators phi could be f, phi could be a scalar, a field in the adjoint, and so on. And we act with derivatives on these two fields, and we can make a primary operator out of this thing, so something which it transforms in an irreducible representation of the conformal group. And these operators will, in a weakly coupled theory, will have a dimension which is typically small, so it will be of order s. So delta will be of order s. So this is not much bigger than, well, you could have, let's say, s equal to 3, for example, and it will have a small dimension. So weakly coupled theories cannot be well approximated by gravity. So you will have really to go to strongly coupled theories, where these corrections that we get, so typically we'll get some corrections to the dimension, which of course depend on the spin. And in theories that have gravity duals, these corrections become very, very big for all the operators that have spins bigger than 2. So getting large anomalous dimensions is fundamental for getting a good gravity dual. That's what I'm trying to say. Okay. So now that we discussed all these operators, we can start computing correlation functions. So in conformal field theories, the natural observable are correlation functions of local operators, of these operators we've been discussing. And one of the main elements of AdS CFT, or an element that is used all the time, is the relationship between correlation functions of local operators and a certain calculation that we'll do in the boundary theory. So let's first start discussing an operator which has high anomalous dimension, corresponds to a single particle of large mass. Then in that case, well, anyway, before we say that, the object we are considering is this, correlation functions of local operators in the conformal field theory. And now let's consider, for example, the two-point function, O of x1, O of x2. Now, by scaling symmetry or conformal symmetry, this two-point function goes like x12 to the power 2 delta times some coefficient, which we can set to 1 by normalizing the operator properly. Okay, if delta is large, then we have this equal to 0. We have, let's say, x, and we separate 2 points by some distance in the x direction. And we have a massive particle in the interior. Massive particle can be, it's well approximated by a geodesic. So we have a geodesic that goes between these 2 points on the boundary. Now, this follows from what I said before, though perhaps not very clearly. So I discussed before that we had these coordinates in AdS space, where AdS space looked like a cylinder. And there was a state that was a massive particle that was propagating along the time direction in the cylinder, right? And we also had this state operator mapping in the boundary theory, where a point here, where we mapped this whole cylinder to radial evolution around this object. So we can view, let's say, one of these points as this point here, and the second point we can view it as some point at infinity, and then we have this particle that propagates along the cylinder, the same particle that we discussed before. All that I'm doing here is making a coordinate transformation that maps those 2 points from 0 and infinity to these 2 finite points here. And then the trajectory of the particle corresponds to just this trajectory. This is a semicircle, and these are the geodesics of anti-de Sitter space or hyperbolic space. Here I'm taking this x to be along a space-like direction, so everything I say here also will hold in hyperbolic space. Okay. And again, that's the simplest way of getting the geodesics in hyperbolic space is to do this mapping I just mentioned. Okay, good. So that's this is the picture. Now, how do we get this result from this picture? Well, we need to consider the bulk theory. Now, in the bulk theory, if we have a particle, we'll have some contribution to the partition function that goes like the action of the particle, right? And this action will be equal to e to the minus m times the length of that trajectory. Now you can come and evaluate this length, and so that's simple to do. As I said, this is just a semicircle. So we have this semicircle. We can have this angle theta. Now the metric is over there. So it's whatever the metric is for a circle, which is just the integral d theta, divided by that factor of c. Since we have the square root of the metric, we have a factor just of c of theta. Okay, so that's the metric we need to evaluate. That's the integral we need to evaluate. The length is equal to this, and we find that it's infinite. Okay. Okay. Well, that's typical. So you always get infinities in conformal field theories, but this infinity is due to the fact that well, we're going all the way to the boundary. The boundary is infinitely far away. So this is just the same as the statement that's of saying that the boundary is infinitely far away. So I didn't mention that, but in proper distance, the boundary is infinitely far away. So in order to do any computation, you really need to, you will need to put some cutoff. You need to put some cutoff at c equal to epsilon, and really compute only up to c equal to epsilon, and then learn to take the epsilon going to 0 limit. Now, this is in correspondence to the fact that in field theories, we have to put some ultraviolet cutoff, compute some quantities, and then take the ultraviolet cutoff to infinity. So what was an ultraviolet divergence in the field theory translates here into sort of an infrared divergence, because here this is due to the fact that the volume or the lengths in AdS are infinite. So it's an infrared story. But it's an ultraviolet story in the boundary theory. And this occurs over and over again. This is just the simplest incarnation. Okay, so you can. So we need to integrate only up from c bigger than epsilon, and so if this has some, let's say, size x, we have to integrate up to a theta, which is of order epsilon over x, and so this thing will give a log of epsilon divided by x. Okay, where x is either this distance or half of the distance. We don't care about these factors of 2. Okay, so what we get is, for fixed epsilon, we get e to the minus m. I forgot the factor of r here, which will give us the correct dimension, times a log of epsilon over x. And this log is negative, so we would better get a positive sign here. Get that. And so here you see a factor of epsilon, which you get epsilon to some dimension. And if we were to keep track of all factors of 2, we would get a 2 here. And so we'll get up to an overall factor that depends on epsilon, 1 over x to the 2 delta, which was what we wanted. So the x dependence is precisely the dependence we had there. The overall factor that depends on epsilon, so this epsilon to the power 2 delta, is something we need to absorb in the definition of the operator. And it's what's given the operator its dimensions. Okay, very good.
Why was geodesic historical?
Yeah. That's an exercise. Yeah, I didn't explain why it was a circle, but it's in the exercises. Yeah, I guess I didn't mention the exercise, but I prepared some list of exercises, and you should get them probably tomorrow or today if we'll do it fast enough. But one of the exercises is to show that the geodesics are a circle. Now, this derivation is perfectly correct when MR is much bigger than 1. If MR is close to 1, again, you have to do the quantum mechanical version of this. So you'll have to sum over all paths and so on, do the path integral. And that's just simply the same as solving the wave equation, solving the classical wave equation in this space. And again, that's another exercise. So the exercise consists of, well, it will be printed. So exercise, solve the wave equation for a scalar field phi. You might find it convenient to start first with massless fields. It's a little simpler. And then put a regularizer at scale epsilon, and you put some arbitrary boundary conditions. So you'd say at c equal to epsilon, you put some arbitrary boundary conditions phi 0 of x, and then you can solve the wave equation. And what that is supposed to give you is the following. So I'm going here to state the final dictionary. So if you calculate in the quantum field theory, you consider the generating function of correlation functions for the operator O that is associated to the scalar field phi. This is an integral in 4 dimensions on the boundary theory. That is supposed to, well, it's approximated by e to the minus the classical action for the scalar field on the classical solution, okay, that you have found by solving the wave equation and setting those boundary conditions at the boundary. Okay. Let me be a little more explicit. So in the bulk, we have an action of the form grad phi squared. If we have a massive field, we also, of course, have its mass. So this is the action. This is the bulk action. So what we are supposed to do is find the equations of motion for this action, solve with these boundary conditions, replace it here back in the action. You will get some terms that diverge with epsilon, blah, blah, blah. And you get also some terms which correspond to the non-local part of the correlation function of this operator. So in other words, when you do this, the easiest way to do it is in Fourier space. So you Fourier transform this phi of p, and so you'll get things. Well, you could also do it in position space, but phi 0. Well, anyway, you can do it in the exercises, or you can ask me questions if you want. Now, I put this here, this approximate sign, but there is an exact version of this relationship. And the exact version of this relationship is given by computing the full partition function in the gravity theory with the corresponding boundary conditions. So the partition function in the field theory as a function of the metric, the 4-dimensional metric, or couplings, and these couplings could depend on the position, and the metric also could depend on the position, is equal to the full partition function of gravity with boundary conditions fixed by the metric, or by those 4-dimensional values of the metric. So there is, for example, a 5D metric, and at the boundary at epsilon is equal to that 4-dimensional metric that was appearing here. So here there is some G4, the 4-dimensional metric. The 5-dimensional metric is set to this value. Okay? And so that's the full dictionary. And in the regime where we can neglect the gravitational back reaction and so on, and interactions between these 5 particles, this is correct. If we had the more complicated action here, which included, for example, some phi cube term, then we'll have also contributions to 3-point functions, for example, right? And in general, there will be a perturbative way to evaluate the right-hand side here in terms of some diagrams, some sort of Feynman diagrams where you start from some points in the boundary where the operators are inserted here at the boundary. These are also sometimes called Witten diagrams, where you have some interaction, phi cube interaction in the bulk, and these lines shall simply denote the propagators from the boundary to the bulk. Okay. Now, okay. Now, it's very important in this story that there we are supposed to sum over all geometries. And we can also include geometries which are different from the original geometry, different topology, but have the same boundary. And the nicest example is the example of a black hole. So a black hole is a geometry which is different than the geometry of the original AdS space, but has the same boundary conditions. So you can consider a black hole inside anti-de Sitter space. It asymptotically, you'll have the same anti-de Sitter space you had without the black hole, but inside you'll have something with a different topology. Now you can also have things which are called black brains. So in this situation where we have the z direction and we have, let's say, the x directions along here, we could consider a black brain, so a black hole which is extended along the 3 spatial directions of the theory. So this is a state that is translation invariant in the 3 spatial dimensions. And there is such a solution. It's given in the exercises, so that's some explicit geometry which here is very similar to AdS space, and it has a horizon here at the position, at this position. So it has a horizon and subposition C0, and the position of the horizon is related to the temperature in the boundary theory. And now, what could be the relation between the position of the horizon and the temperature? Do you need to do any work to find this relationship? At least the scaling? What determines the relationship? Is it, for example, temperature to the 3, temperature to the 2, to the -1? Right, it's determined by scaling, right? So we need to understand under a dilatation symmetry, T scales like mass, C we said scales like length, so with -1, okay? Okay, no work, that's nice. Okay, there is a numerical coefficient which you cannot get through this argument, unfortunately. Now then we have the free energy, which can, well, obviously now that you learn how to calculate this using scaling, you also know how to calculate this guy. And so how do you calculate this one? Well, first of all, you need to make an important assumption, well, which is kind of obvious, which is the fact that it will be proportional to the volume in the 3 dimensions, right? So it's infinite because we'll have infinite 3-dimensional volume. So it's proportional to the volume in the 3 dimensions. Right? And well, so this is the total free energy. So this is the thing that appears in the action. It's dimensionless. And so the rest, of course, has to be beta to the -3 or t cubed. Okay. And then there is some coefficient here in front. Okay. Now, what will the coefficient in front be? How much calculations do you need to determine this coefficient in front? So we would like to understand the dependence on the Newton constant of the coefficient in front. So this is some calculation that will come from evaluating the action of some solution. The action is just the action of the Euclidean version of this black hole that will give us the free energy. And it is, well, the action of gravity is 1 over g Newton times the action, I mean the usual action, square root of gr plus blah, 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 right? So one thing we see is that, well, it will involve 1 over g Newton. So because it's whatever action we had there, none of what we said so far depended on g Newton. The black hole solution doesn't depend on g Newton. We'll evaluate this, we'll get something, and we'll have some g Newton in front. Of course, the something we get here is what's going to give us this part, right, that we already determined. And all we are determining now is 1 over g Newton. Now, but g Newton is an object which is dimensionless is dimensionful in the bulk theory, and it should become dimensionless by absorbing powers of r, the radius of AdS. Now, dimensions in the bulk are not related to dimensions in the boundary theory. That's important. So we're not going to cancel the dimensions of g Newton by some power of t. That doesn't work. Because recall that the rescaling, what it does is an isometry in AdS, right? It acts as isometries in AdS. They don't have any dimensions, if you wish, from the bulk point of view. So these dimensions of this guy have to be fixed by powers of r, and in 5 dimensions, just at r cubed. Anyway, so this is a prefactor. And now if you compare this with a free field theory, so in a free field theory, you get something similar to this. So beta f is something similar to this, except that you have the effective number of degrees of freedom. So, right? So I mentioned in the beginning of the lecture that the effective number of degrees of freedom is proportional to this number. And if you wish, this is the derivation of that fact. Okay? So when we consider the thermal partition function of this object, which is computed, the thermal partition function of the boundary theory is equal to the Gibbons-Hawking partition function for the gravity theory, corresponding to this black hole, and we get this answer. And are there any questions? Now, in theories that come from gauge theories, this number is typically going like n squared. Of course, in the free theory, we can calculate it. But in the bulk theory, well, we have this formula, but we can't necessarily match the numerical coefficient. The numerical coefficient could be some function of the 't Hooft coupling, which in principle we have to compute. Yeah, I guess maybe at this point we can make this plot. So as a function of lambda, you can calculate that n effective over n squared. And for one particular example of this duality, which is the case of n equal to 4 super YAMLs, which we'll discuss in detail tomorrow, we find that if we call this 1 here, that's the value at weak coupling. This is a function of the 't Hooft coupling, which goes between 1 and 3/4. And we really only know these two parts of the function. So we know what it is at very strong coupling. We know the first string correction. We know what it is at very weak coupling. And we know the first correction there at weak coupling. Now, what I'll discuss tomorrow, I'll discuss similar calculations, but of anomalous dimensions of operators, where we can actually compute the full function that interpolates between weak and strong coupling. Okay, so far we've been discussing, one more thing to say about these black holes. Let me kind of erase probably here. We can calculate correlation functions in the presence of a black hole. And so if we have this black hole, and we compute the correlation function. So as we said, the correlation function corresponds to the emission of a particle, and then a reabsorption of the same particle. And now, if you emit a particle and there is a black hole, what will the particle want to do? Yeah, it will want to fall into the black hole, of course. So it's very unlikely that the particle would come back out, right? And the longer you wait, so if you send it in and you say, oh, wait, I want to detect you back, then probably the fact that you have the black hole doesn't matter too much. But if you wait for a long time, then it's very unlikely you will see the particle. So in fact, if you compute such two-point functions, you find that they will decay exponentially with time. So this is some time t. With some number and to compute the number, you really need to do some calculation. Well, of course, you can compute how it depends on the black hole temperature. That's not too complicated. Same story that we discussed before. But the precise numerical coefficient, you have to do some calculation. Okay. It's some number, actual number, divided by beta. This is the same as what we discussed before. And that's how they will decay. So they decay because the particle wants to fall into the black hole. And in the language of black holes, what happens is that this long time tail, so this number here, is related to the so-called quasi-normal frequencies of the black hole. So here you can consider excitations around the black hole. And they're not quite energy eigenstates because they're falling to the black hole. So the frequencies of those eigenstates have a real part, and they also have an imaginary part. And this imaginary part tells you about these long time tails. Okay? Good. Now, in the particular case that you choose this operator to be the stress tensor, this correlation function tells you something about how the black hole responds to small pushes. So you push the horizon a little bit in one direction, and then the fluid, this thermal fluid in the boundary theory, will respond in some way. Or the horizon itself will deform in some way, and it will lead to different expectation values for the stress tensor at later times. So you can view these two insertions of stress tensor as saying, well, you deform the metric a little bit to give a little push to the fluid, and with this one, we just measure how the fluid is moving. Well, I guess I'm probably going a little fast, but I probably should have mentioned that, of course, this finite temperature configuration is breaking the boost symmetry of the problem, right? So you have your 4-dimensional conformal field theory. You raised it to finite temperature. Now it's filled with some thermal gas or fluid. It's not really a weakly interacting gas. I mean, it's something where the particles are interacting very strongly. And now this fluid will have properties. As any good fluid, it will obey the Navier-Stokes equations and so on. And you can calculate the coefficients appearing in these Navier-Stokes equations, like, for example, the viscosity, by doing such calculations. So the viscosity tells you how you are dissipating energy, and these exponential tails are related to that. So they are related to how, if you shake this a little bit, how quickly that the information about that shaking dies out, and that's related to dissipation. Now, in general, the slogan is that falling into a black hole is the same as dissipation in the boundary theories. In the boundary theory, you have this thermal gas, and you start with some excitation, localized excitation, and this excitation slowly thermalizes and becomes equilibrated with the rest of the gas. And that process is described in the dual gravity theory by a particle falling into the black hole. Okay. So you can compute this viscosity, the shear viscosity, which is the only viscosity you have in a conformal field theory, and it's related to the absorption of gravitons. And absorption of gravitons by a black hole are proportional to the area. But now you remember that the entropy is also related to the area, so you think that it might be a good idea to divide this viscosity by the entropy, and indeed you get some number, which this turns out to be a pure number, which is 1/4 pi. And this is a general result in any theory that has a gravity dual, and it's correct only in the gravity approximation. So once you start including corrections, higher derivative corrections to gravity, this gets corrected, and could get corrected with plus or minus. Okay. What time am I supposed to stop? Now or? Okay. As I wish. Okay. Well, the one thing I wanted to mention is go back to the original diagram for the warp factor that I drew, and try to say what it corresponds to. So in the beginning, we drew a warp factor which had some minimum here, right? Now, this is the typical situation you'll get when you consider confining theories. So some theories where there is no mass gap. I mean, such a warp factor does not have the conformal symmetry anymore. So these theories will have a mass gap. Now here, the warp factor is not that it goes to infinity again, but in the typical situations, what happens is that the space ends here. And there are different ways in which a space can end. Typically, in the examples, there are some extra dimensions, let's say an extra circle, which has some fixed size here at infinity. And then when you come here, it shrinks in a smooth way together with the radial direction in such a way that gives you smooth geometry. So that's one way it can work. I mean, but basically, the space ends here. And then if you consider a particle, the minimum energy for a particle of mass m will be achieved here at the minimum. And that minimum energy is non-zero. So any excitation you typically want to put here, even a massless particle like a massless graviton, will be forced to have some wave function which is localized in this direction. For the same reasons that we saw in global AdS, so this energy will be non-zero. And from the point of view of the 4-dimensional theory, you'll have a non-zero mass for the particle. So in this situation, you typically have a mass gap. Now, sometimes in some very specific examples, there might be massless degrees of freedom that have to do with flat directions of the field theory and so on. But the typical situation without supersymmetry and so on is to have a mass cap. Unless, well, typically, if you don't have a mass cap, there is some good reason. Either supersymmetry is protecting it, or maybe there is some broken, spontaneously broken symmetry or something like that. Now, I mentioned that a massless 5-dimensional graviton gives rise to a massive spin-2 particle in 4 dimensions. And you can do the counting of degrees of freedom to check that indeed this is consistent. The numbers match between 5 and 4 dimensions. Now, okay, so a few more words about the radial direction. I think I can't emphasize enough, perhaps, the importance of understanding this connection between positions in the radial direction and the sizes and so on the boundary theory. So let me emphasize it once more. We mentioned that we have this metric. This is the metric of AdS. And all the computations that we do usually that we do when we match to field theory quantities, we are typically looking at something and approaching the boundary at fixed distance x. So we will approach the boundary at fixed x distance. This is sometimes called comoving distance and so on. I mean, it's called like that if you think in terms of the Sitter space. So this metric is very similar to the metric of the Sitter space. So ds squared, this is AdS. The Sitter space is the same thing, except that there's a minus sign, so d eta here. And so now we typically is drawn like this. Eta here is less than 0, is conformal time. Again, an infinite time to the boundary. The boundary here in the Sitters is at infinite future. This is just describing an exponentially expanding universe. It's exponential once you here go to the log of eta. So it's exponential in the log of eta. It's a power here. And we have, this is the end of the Sitter, and here is the very far past. And again, these fixed x coordinates correspond to what's called fixed comoving distances. So if you have two observers who are just following geodesics, they would follow these fixed x distances. Okay, now you are probably familiar with the fact that in the Sitter, these distances go to infinity in the far future, and the proper distance goes to infinity, and here again the proper distances go to infinity. Now, in the case of the Sitter, we know we have horizons, and that anything and this whole region becomes causally disconnected from the observer that is sitting here, and so any perturbation that we do here will not affect the observer that is over here. So these two universes will, once they will reach a certain time, they will evolve sort of separately. So this is a separate universe argument. Now here we have exactly the same story governing this behavior as a function of the cutoff. So we do some calculation at fixed x, and then when we start moving out, the same reasons that here lead to the separated universe, blah, 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 imply that the evolution as we change epsilon is going to locally affect each of these two guys separately. Okay? And that's why we can extract, so if we are computing, for example, correlation functions, we can absorb this whole evolution in epsilon as some local renormalization of the operator and so on. And it's also related to the fact that we get a local field theory on the boundary. So we have the possibility of just changing arbitrarily the metric here. It will not affect how the metric is approached, how the limit is approached here. I mean, it will affect non-local correlations, but not the local behavior of the theory. So now there are many similarities between the Sitter and ante-de Sitter, and many of the perturbative calculations you can do are identical, and you can translate very simply between one and the other. Now there are some differences, and some of the differences are that, well, we can choose examples where anti-de Sitter is completely stable, will not decay, but de Sitter, in all the examples we know, string theory, will decay, and there are good reasons for thinking it will always decay. And well, also in the case of anti-de Sitter, there are examples where we know the dual conformal field theory. In anti-de Sitter, we know the dual conformal field theory. In de Sitter, we don't know whether any conformal field theory really exists or not. But one thing I can't resist mentioning is the fact that the quantity that appears there, C gravity with fixed boundary conditions, is just nothing else than what you would call the wave function of the universe. So if you let me draw this picture this way now, we have now a Euclidean space, let's say hyperbolic space, or some locally hyperbolic space. It could be globally different, or we could have perturbations, blah blah blah. And that quantity there should be viewed as the wave function with some fixed metric here on the boundary, right? So that's another way of thinking about that object, C gravity. Of course, it's the wave function of the universe in some Euclidean regime. The one that appears in de Sitter is the wave function in the Lorentzian regime, more, well, real time, where things happen. Okay. And so now I'd like to mention one more thing, one more general thing. And that's about global symmetries. So we often encounter field theories, quantum field theories, with global symmetries. Now imagine you have a quantum field theory with a global symmetry. Then there is the corresponding current, conserved current. And it turns out that in the dual AdS space, you'll have the current is associated to gauge field, a mu. Well, this a mu now has 5 indices rather than 4. And so we have corresponding gauge fields. So global symmetries on the boundary correspond to gauge symmetries in the interior. And that's good because global symmetries are exactly conserved, right? They cannot be violated in the boundary theory. But we know that if we had a global, just purely a simple global symmetry in the bulk, black holes could violate this global symmetry. The formation and evaporation of a black hole could, in principle, violate these global symmetries. But the formation and evaporation of black holes cannot violate gauge symmetries. And so that's at least one necessary consistency condition for this to work, is that these global symmetries are carried by gauge fields, which black holes can also carry. So they can also carry global charges. And well, similarly, if you have a supersymmetry, you'll have supergravity, and so on. Okay, I think I'll stop here and continue with more details. So the next 2 lectures will be about n equal to 4 super Young-Mills, and we'll discuss that case in great detail. Okay, thank you.